We've had clear scientific evidence for over 50 years that the hot Big Bang marked the beginning of the universe as we know it. Initially, the universe was smaller, hotter, denser, and more uniform. Now it's expanding, cooling, and filled with clumps like planets, stars, and galaxies. Everything we see today was once condensed into a single point or singularity, marking the start of space and time. If we trace back to the earliest times, however, recent insights suggest the Big Bang might not be the actual beginning. How fast is the universe expanding, and will everything eventually cease to exist? Let's explore. Across the spectrum of wavelengths from radio to gamma rays, we find stars, galaxies, gas clouds, plasmas, and radiation in every direction. But where did it all originate? Although the universe is filled with matter and energy everywhere and at all times, it's logical to assume it had a starting point. Thus, we must ask the cosmos about our cosmological origins and heed its response. Currently, the cosmos is expanding, thinning out, and cooling down. Physics principles enable us to trace backward just as easily as forward. Long ago, the universe was denser, hotter, and smaller. But how far back can we go? In mathematics, the temptation exists to push boundaries infinitely toward infinitely small dimensions, densities, and temperatures of singularity. The Big Bang concept envisioned a single beginning for space, time, and the cosmos. However, a closer look reveals a different story. The theory of general relativity by Albert Einstein, proposed in 1915, underwent rigorous scientific testing, revealing limitations. Like many scientific narratives, the Big Bang's origin is rooted in theoretical and experimental fields. Einstein's theory, challenging Newton's idea of gravity, quickly yielded precise solutions, including defining black holes and describing an expanding cosmos. The discovery of rapidly moving nebulae outside our galaxy supported the idea of an expanding universe. Thus, while the Big Bang once seemed to mark the universe's beginning, our deeper understanding suggests otherwise. In the 1920s, Edwin Hubble began calculating distances to individual stars in nebulae. Not only were they much farther away than anything else in the galaxy, but those at greater distances were also accelerating away from us. This realization led to the understanding that the universe was expanding, as confirmed by luminaries like Robertson and Hubble. In 1927, Georges Lemaitre was the first to project this expansion backward, envisioning what he termed the primeval atom. He recognized that everything around us originated from this early era when the universe was a hot, dense, and expanding mix of matter and radiation. Further development of this idea led to predictions. As we look farther back in space, we peer further back in time. Therefore, objects from that era should exhibit certain characteristics. They should be less evolved, less gravitationally clustered, smaller, and composed of lighter components. Crucially, there shouldn't be more galaxies or stars. Instead, there should be a remnant, a cool and sparse bath of cosmic radiation from a time when atoms couldn't form due to intense radiation. The concept of Big Bang nucleosynthesis suggests a pre-stellar phase where nuclear fusion occurred, resulting in a dispersion of light elements and isotopes throughout the cosmos before stars formed. These ideas, along with the expanding universe, form the basis of the Big Bang theory. The evolution of the universe's large-scale structure, specific galaxies, and their star populations all align with the predictions of the Big Bang. The primary evidence supporting the Big Bang theory came with the discovery of cosmic microwave background radiation, a remnant from the early universe. This radiation, only slightly above absolute zero, along with its temperature irregularities, provided crucial confirmation. Our ability to extrapolate back in time based on evidence is a significant achievement for science. The physics of the hot Big Bang's initial moments left marks on the universe evident in its large-scale structure and the cosmic microwave background. However, extrapolating beyond the bounds of evidence into a singularity is risky. Arbitrary high temperatures, densities, and volumes would have effects on our universe unsupported by evidence. For instance, if the universe emerged from a singularity, it would require precise initial conditions to balance expansion rates and matter-energy content. The absence of magnetic monopoles as predicted by high-temperature conditions and uniform temperatures everywhere present further challenges to the singularity hypothesis. Cosmic inflation provides a more plausible explanation. It extends the hot Big Bang back to an early hot, dense, and uniform state but stops short of the singularity. Inflation suggests a mechanism to set the cosmos parameters, ensuring balance in expansion rates and matter-energy content. This explanation is more satisfying to scientists who seek causes for observed phenomena rather than relying solely on initial conditions. To eliminate any existing high-energy remnants and prevent the universe from becoming too hot, inflation proposes a phase preceding the hot Big Bang dominated by a cosmological constant or similar mechanism. This phase occurring before inflation ends and the hot Big Bang begins stretches the universe flat, giving it uniform qualities everywhere and preventing the creation of new high-energy remnants. Quantum fluctuations during inflation generate predictions for the flaws the universe would have at its beginning. Since its proposal in the 1980s, inflation has been tested against alternatives, including a universe emerging from a singularity. The results overwhelmingly support inflation. It reproduces all the successes of the hot Big Bang and explains puzzles that cannot be solved solely by starting conditions in the hot Big Bang. While an inflationary universe cannot be extrapolated back to a singularity like the hot Big Bang, it also cannot lead to one on its own. This challenges the notion that the universe began from a singularity, forcing a re-evaluation of our understanding of cosmic origins. Observations support cosmic inflation as preceding the hot Big Bang. Any prior elements of the universe were inflated away during the exponential growth phase. When inflation ended, the universe transitioned to a hot, dense, and expanding state. However, crucially, inflation erases knowledge of events prior to its termination. We're left with uncertainty about the true origin of the cosmos, whether a singularity preceded inflation or if there were other phases before or after inflation remains unknown. We must acknowledge our ignorance until we find ways to extract more knowledge from the universe. In summary, while the Big Bang did occur a long time ago, it wasn't the absolute beginning as previously believed. Inflationary cosmology challenges our understanding of cosmic origins, leaving us with more questions than answers. Thank you for watching another episode of InfoPaper. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.